So this is Physics 1C for Tuesday, March 9th, and we're going to be talking about electric potential, and I guess hopefully what you can hope to kind of learn from today's lecture is you should be able to say by the end of today, you know, what the word volt means, like what a volt is, like when you go buy a battery, like a 9-volt battery. You should have an idea of what that means, and maybe an idea of what voltage is. Basically the same concept, as well as being able to define what energy is for systems with electrical charges. So that's really what today is about. The title of this chapter is Electric Potential, and that is definitely what we'll be talking about, but something to keep in mind as we're doing this is that really what we're talking about is energy. That's really what we're talking about here today is energy. Okay. So yeah, let's get to it. The first thing to do is to define what electric potential energy is. So let's do it. And we're going to do it in the same way we defined what gravitational potential energy is, if you happen to remember that. And if you don't, I'll go through it and we'll do kind of an analogy between the two because they're very similar. Okay, so electric potential energy. So let's say you have a system where you have like an electric field, okay? And let's say that this electric field looks like this. Let's make it green. So you've got some electric field lines, and they all point downwards. And we'll say it's just like a uniform electric field to keep things pretty simple. So we've got electric field lines like this. That's probably enough. So this is our electric field. And of course, this electric field has the tendency to cause charges that are placed within it to move. So for example, if we were to place a positive charge inside of here, and we say it carries a charge Q, we know that that charge is going to feel a force. And just to remind me, what direction is that force going to be due to this electric field?
Downwards.
It'll be a force that goes this way, right? We call that the electric force. And the size of that force, what's the size of this force equal to in this case in terms of the variables that I've written here on the board?
Q times E, magnitude of E.
Right. No, Q times E, that's right. You don't have to do the magnitude because the vector direction of the force is the same as the vector direction of the field, right? And the charge here will tell you what direction it goes. Like if it's positive charge, it's down. If it's negative charge, it just flips it and it goes up, right? So anyway, that's the direction of the force, right? Now, any force can do work, right? So the electric force or the electric field, however you want to think about it, can do work, right? So we're calling this charge Q. The electric force can do work on that charge, right? And it's pretty easy to define how that work would be done, right? So if you don't remember, work requires two things. You need to have a force, and you also need to have a displacement of some kind, okay? So delta R is like the change in position of an object. So as long as you have a force and you have a displacement, you can get work. So W here stands for work, not weight. So in order to have this charge have work done on it, it's going to have to move across some distance. Okay? And let's say that it moves downwards maybe. And how do we want to do this? Let's say that we define this point right here to be y equal to 0. And let's say that our object starts off at some position, and we say that the y-coordinate of that point right there is just going to be, I guess we would call it like y0. And let's say that it moves down to here to a y-coordinate that we call maybe y1. So the particle goes from y0 to y1. So the displacement of the particle is going to be, let's use an actual vector for this. The displacement of the particle goes this way. we call that displacement maybe delta y or something like that. All right, so then what we would have is that the work done on this particle would be equal to the size of the force, which in this case is the electric force. So this is equal to Q times the electric field. And we would dot product that with the displacement, which in this case is delta y. And when we do this dot product, I don't think we've talked about dot products in this class yet, have we? Yeah, we have, because we just did the whole chapter on Gauss's law. Okay. So to do dot products, right, you just take the size of one vector, the magnitude, and you multiply by the magnitude of the other vector, in this case, just delta y. And yeah, that's pretty much it, right? In this case, you'd also multiply by the cosine of the angle between the two of them, but the angle's 0, so this just becomes 1. So yeah, so you just end up getting, as a final result, that the work is equal to Q times E times delta y. Now, do we want to make this more complicated yet? Probably not. Let's just leave it like that for now. So that's our definition of what the work is. And our goal here is to basically use this to get some information about the change in potential energy. So we use the symbol U to represent potential energy. So the delta here means this phrase here, this mathematical expression says change in potential energy. Now, what we know is that certain types of forces we can define a potential energy for. If you think back to physics 1A, what are the forces used in physics 1A? What are examples of forces from 1A that have potential energy expressions associated with them?
Spring forces.
Spring. What else? Kenny, did you say something I didn't hear?
That gravity.
Gravity, yeah. So the spring force and gravity, and I think that's it from 1A. And that means that all of the other forces that you discuss in 1A do not have potentials, right? Electric potential, or they don't have potential energies, right? So things like tension and friction and a thrust force from a plane or the force of an engine in a car, basically almost all the forces you deal with in physics 1A, except for weight, which is gravity force, and springs. All of those forces fall into a certain class. What are all the forces that you don't write potential energy down for? What are those? What kind of forces are those? Does anyone remember?
Non-conservative?
Non-conservative.
Yeah, non-conservative forces. Okay, so it turns out that the electric force is a conservative force, just like gravity. And that means you can write a potential energy down for it. To remind you what a conservative force is the type of force where the work done by the force is independent of the path that you take, right? And what that means is basically like if I take an object like a pen and I lift it from this location up to here, am I still on screen? Let me just switch where I can actually see what I'm showing you. Yeah, so if I take a pen, this is hard to see. Let's use this cup instead. Can you see that? Yeah. So I take a cup and I put it at the bottom of my video camera here, and I move it up to the kind of top right here. That requires work done by me, but it also has work done by the gravitational force, and that's what we're interested in. So when you lift an object upwards, and you go from one location to another, for it to be a conservative force, what has to happen is that it takes the same amount of work by the field, no matter what path you take. So if instead I start down here and I move in this direction, and then I move up, it takes exactly the same amount of work, because when you move laterally, like this way, gravity doesn't do any work. When you move up, gravity does work. So whether you go along like a diagonal line like this, or you move along a straight line from here up to here, gravity will always do the same amount of work because I'm moving between the same like kind of two elevations, right? And the electric field's no different, especially an electric field that's oriented like the one that we've drawn here. It's really easy to see. Oops, didn't mean to do that. It's really easy to see that the only way that the electric field is going to do work is if you move either in the same direction as the field or the opposite direction as the fields. If you move left and right, can you all see that the gravitational field just wouldn't do any work in that case? Does that make sense? If you move left and right,
Yeah.
the force can't do work because of this piece right here. When you move left and right, your angle is going to be 90 degrees. Okay, so because the electric field is a conservative force, we can define a change of potential energy, and there's a direct connection between the work done by the force and that change of potential energy. Does anyone know what the connection is? How is this work related to the change of potential energy? Okay, if you don't remember, I'll give you an example to help you understand how it works. So if we take just the exact same example we just did, here so I can actually see this. So if I take this cup, right, and I move it upwards, what is the sign, it's like positive or negative, of the work done by gravity? So if I go from the bottom upwards.
Oh, it's negative.
Yeah, negative.
Does everyone understand that? That gravity would do negative work because the force of gravity is down, but your displacement is up. So gravity does negative work, right? And the other way you can think about it is that you need to do work to lift it, right? Gravity won't just lift an object up. That's why it does negative work.
So it's negative, the change in potential energy.
Yeah, that's right. So we're not. I want to kind of actually explain it though, so everyone understands, because I think this is something that not everybody remembers from Physics 1A, and your teacher may not have even talked about it. So what about this? So again, so when I take an object from this lower location and I lift it upwards, we all agree that the work done by gravity is negative. So the next question would be, does the object gain or lose potential energy when we go from here up to here? Does it gain or lose potential energy? Can you all just type an answer in the chat, maybe?
Gain?
Yeah, it gains energy, right? If you go up, you're at a higher potential energy, right? Okay. So it appears that when the work done by gravity is negative, the object gains energy, right? It's like there's an opposite thing going on there, right? So potential energy goes up, but the work done by gravity is negative. And then we look at the opposite situation where we start from the top up here. If we let the cup kind of move downwards like this, what's the work done by gravity? Is it positive or negative? Positive, yeah. So when you go from here downwards, you actually have to stop gravity from pulling it too quickly, because gravity is doing all the work for you now. It doesn't mean that you don't have to exert energy to do this. Obviously, if you lift things up and down, that's how people lift weights at gyms to, make their muscles strong or whatever. But when you take an object from this location and you let it fall downwards, though, it loses potential energy, right? So again, when work done is positive, the object is going to lose potential energy. When work done is negative, the object's going to gain potential energy. And that gives you the relationship that Cam said. It's a really simple relationship. The relationship states that the work done by the force should be equal to the negative of the change of potential energy for the force. That's our relationship, right? Now, we know what the work done here is. Let's kind of change colors here. So the work done is given by this. And, change in potential energy is just, it is what it is. It's just negative delta U. Now, we can write this expression out in kind of more detail. I'm going to write it like this. QE. Delta Y can be written as something like, let's say, as I wrote it over here, I said this was our final position, Y1, and the initial position was Y0. So this is going to be something like Y1 minus Y0. The left-hand side, the right-hand side of this equation would be something like, we'll just use the same 1 and 0. It's going to be the potential energy at one location minus the potential energy at another location. And then you can kind of make this identification from the left-hand side to the right-hand side based on what's being said here, you can identify that, for example, this term here and that term there, see how it's QEY1 and negative U1? That's going to be a way to define what the electric potential energy is. So it's going to be Q times E times Y1, or just Y in general, should be equal to the electric potential energy. So this is a way to describe electric potential energy. If I write electric PE, I think you'll understand that I mean potential energy by that. QE times Y. Now, let's compare this to gravity, because we can also write a similar expression for gravity, right? With gravity, certainly everyone remembers this. This is one of the things you learn probably in really early physics classes, not necessarily even at college. What's the potential energy due to gravity?
Just mgh.
Just mg times h, or let's use y as well so we can see why it's exactly the same. It's mgy. That's what it is, right? That's the potential energy due to gravity. When an object's elevation increases, you gain more and more energy, right? The higher you lift an object, the more potential energy it gains. And what is that potential energy? It's the idea that if you were to let the system do its thing, that energy would basically make the object move downwards and cause it to basically gain kinetic energy, right? So it's exactly the same concept. It's 100% the exact same concept. If you understand potential energy due to gravity and how and why and where we use it, right? Actually, when did we use potential energy due to gravity? When was it useful? How did we use that idea in physics 1A?
To find like kinetic energy.
Yeah, in general, we kind of use the idea of potential energy along with kinetic energy, along with whatever other types of energy you might have. In 1D, you gain the concept of thermal energy, so objects can gain thermal energy as well. We learn about that in physics 1A because when an object slides across a rough surface, the friction that tends to slow it down does work, and it has the effect of transforming some of that kinetic energy into the internal energy of the atoms. And as a result, when you rub things together, when there's friction, things tend to heat up, right? That's another kind of energy. But energy in general is just a way of describing physical systems. It's a way of describing the world and describing how systems move from one position to another, such as a ball rolling down a hill. And all of it's connected together through the work energy equation, right? Work done by non-conservative forces is equal to the change in mechanical energy of the system, right? And it's a really powerful idea that we can use to solve very complex problems that we otherwise wouldn't be able to use Newton's theory of like Newton's Newtonian mechanics to solve, like F equals ma. Things like roller coasters and stuff like that. Okay, so that's electric potential energy. Very similar. You've got a charge. Compare that to the mass of an object, because mass is what makes things feel gravity. Charge is what makes things feel electric forces. And then you've got the field itself, which for gravity near the surface of the Earth, you've got G. And for the field with electricity, you've got E, right? And then the elevation, okay? Now, the only reason elevation shows up in this case is because I designed this particular setup to look exactly like the gravitational field of Earth, right? This electric field, which points downwards, is similar to the gravitational field of Earth, right? So really, this is really only the electric potential energy for a uniform field. That's a bad color. Now, one thing about this is that the absolute number that you get for electric potential energy is kind of meaningless. It's really changes in energy that we care about, right? Because this decision to make this point right here, y equal to 0, is completely arbitrary. That means that two different people doing the same problem, if you were to ask them what the energy at a point was, like if I asked someone to define what the energy at this location is right here, it's going to depend on what their y-coordinate axis system is, like what they chose y equal to 0 to be. So it's really the changes in energy that we're going to be most concerned about in this particular chapter, okay? So that's energy. And from here, we want to get to electric potential itself. Okay? And the way we go about doing this is pretty simple. We take this equation right here, okay? The equation that says that Q times E times delta Y is equal to the negative of the change in potential energy. And what we're going to do now is something we did with forces in the last chapter. In the last chapter, or the first chapter, what we did was we basically took force and we divided by charge to get electric fields, right? You can see it right up here. That if I rearrange this equation to get force divided by charge, then I've now actually defined what we said an electric field was, right? It's the force per unit charge. The units of the electric field are newtons per coulomb, right? So it's force on top divided by charge on bottom. We're going to do exactly the same thing to define what voltage is, or to define what electric potential is. We're just going to divide both of these equations by Q. So what we're going to get is, I'm going to move the negative sign. So it's now going to say negative E times delta Y, okay, is going to be equal to delta U over Q. And then we'll define delta U over Q to be equal to the change in electric potential, okay? So this symbol, delta V, this represents the change in electric potential. Something I probably should do, just to kind of clarify what's going on here. When we took this dot product right here, I removed the vector symbol from the top of this, but just to be like 100% clear, you really, I think, you need the absolute value signs around these delta y's. Maybe you don't. I'm not. Let's ignore that for a second. Let's not worry about that for right now. Okay, so this is going to be change in electric potential, delta V. Okay, and the units for this are going to be joules per coulomb, because you can see right here that this says that 1 joule, which is what we measure potential energy in, divided by coulomb, should be equal to 1. On this side, electric potential, which we use the symbol V for, capital V, is volt. So 1 volt is 1 joule per coulomb. Just like for electric fields, we use newtons per coulomb. For electric potential, we use joules per coulomb. Does that make sense?
Yeah, it does.
Anyone have any questions? So now we know what a volt is. We know it's a type of unit of energy, but it's not just regular old energy. It's energy per unit charge. So to actually get something out of this concept of voltage, you need to accelerate charges, okay? So a volt is going to have the effect of giving some energy to charged particles. And once those charged particles have some energy, you can use them to do work for you, right? So as a, I don't know if this is simple, as a kind of direct example of what this means, suppose I take a battery, right? And I tell you that this battery has a voltage of 9 volts, right? What does the J stand for? Prince Ali, it stands for joules. Energy, basically, units of energy. So suppose I have a 9-volt battery. What does that mean, 9 volts? Well, it means I have 9 joules for every coulomb of charge that is allowed to kind of pass through this system here, right? So if I have a battery and this is the positive end and this is the negative end, the way we get the battery to do things for us, right, is you basically connect a wire here, right? And you connect a wire to both sides. And then in the middle, you put something here. Like, for example, maybe you have a really simple electrical circuit where all you have is just a light bulb. Okay? So you've got a wire that comes in here. It connects to the fitting for the light bulb down at the bottom. And maybe there's an actual stand here that the light bulb's plugged into. But for now, it's just, there's a light bulb there. And then there's going to be a little tiny filament. Thinking of like an incandescent light bulb right here. a little tiny filament that goes in here. And basically what happens is that since I have 9 volts here, that implies that I can push charges through the system, right? I've got 9 joules for every coulomb that passes through. And so the effect is the charged particles are going to start being pushed around this system. They're being given an energy, right? Think of it as like they're given an amount of kinetic energy. And basically, every time that you go through the battery here, the charge gets like a kick of energy as it goes from this end of the battery over to this end of the battery here. Okay, so for every coulomb that passes through the battery, the charge comes out on this side with 9 joules of energy. Does that make sense? So if this is 1 coulomb, every one of these represents 1 coulomb, right? And they're all being pushed through the system. What happens is that they start off with 9 joules of energy over here. They use up all their energy just to get back to this point. And at this point, this charge is going to have 0 joules of energy. And then it passes through the battery, which basically picks it up, does some work on it, right? And it X's out the other side with a bunch of energy. And then that energy basically carries it back around to here. Does that make any sense? There's some other concepts going on here, like we need to define what electric current is too, the rate at which these charges flow. But as long as you understand the idea that the battery endows the particles within the system with energy, then you can understand that that energy basically can be converted into like kinetic energy, and then it can be converted into light energy from the light bulb. And in between, it's actually going to convert to radiant energy, like into thermal energy, because as these charges pass through the light bulb, they get really hot as they try to pass through this piece right here. And that heat then dissipates energy, which turns into light energy. We'll go into a lot more details about how this process works, but now that we have the word volt, we should at least apply it to something that you have seen before, I think. Does that make sense?
Mm-hmm.
So when you plug anything into the wall, what the wall is doing for you is giving you energy. But you all knew that already, right? You all knew that that's what you were doing when you plug something into the wall. This isn't new, right? You all knew that the reason why we need electricity is because the electricity will provide energy for our devices, right? So now we just know one of the vocab words, you might say. It's one of the vocabulary words for how to talk about that energy, and that word is volt, right? So in America, we have these wall sockets, and they provide us with 110 volts, something around there. Realistically, you could get up to 220 volts, depending on how it's connected. When you connect up a normal device, such as a computer or a lamp or a speaker or something, and you connect it up to your wall socket, then you're getting 110 volts of energy out of it, basically. It's not really energy. You're getting 110 volts.
So
Go ahead.
now one coulomb is a lot of charge.
Sure, absolutely. This is a completely ridiculous example for sure. But it's just the numbers work a lot better.
Okay.
Basically. Yeah, the reality is the things that are truly moving through this system are electrons, right? So they're gaining the electron charge multiplied by this. That's how much energy they're gaining, right? But they're also really tiny, so they don't need much energy to move, right?
Mm-hmm. Mm-hmm.
Yeah. And ultimately, we're going to care a lot more about the rate at which these batteries are providing energy than we are going to care about the actual amount of energy they provide, right? Because if you think about it, anytime you plug something into your wall socket, it's providing you like a steady stream of energy, right? And what is that energy? It's basically the motion of electrical charges through wires. And luckily for us, as we've learned in previous chapters, conductors, which is what the wires are made out of, what is it that makes a conductor a conductor? What is it about a conductor that's unique?
It lets charge flow easily.
Yeah, it lets charge flow easily, right? So that's one of the cool things about electricity is that when you connect a wire to a socket, the piece of the system that does work for you are those free electrical charges that exist within the conductor, right? Those are the things. They're like your little worker bees that run into your computer and light up all the circuits and then run back into the system to get energy. You know, so where was I going with that? But yeah, the rate.
So
It's the rate that we care about more. The rate at which your system is supplied with energy, right? In order to get a light bulb to light up to the proper brightness, you need to have power supplied to it at a proper rate. Yeah. So. Okay. Do you all have any questions before we start to make this stuff more complicated?
so this happens through chemical processes.
It might. It might be chemical processes. I mean, so what do you mean? What happens through chemical processes? What
Like
happens in the battery?
like the battery is like raising. I mean, in my mind, I'm kind of like thinking like, oh, the battery's like actually like lifting the electron. Well, that's
Yeah,
just
it
because
is.
like
It
making
is.
an analogy.
Yeah, yeah. It's a good analogy though. It's similar to what's happening. It's basically taking the electron from a position where it has no energy to a position where it has some energy, and letting it go. Now the actual
Where's
process.
that from?
What?
But where is that potential coming from?
So
Or
it's coming through chemical processes, like you said. It's coming through chemical processes, just like you said.
because like
In
it
the
makes it like
case of a battery, and I don't know if it's linked on the. I can't remember if I linked it or not, but there's some excellent videos on YouTube that will give you really nice visuals as to what's actually happening with batteries on the inside. But
okay.
I'll say this much: every type of electricity source that you use has some method of lifting these charges from a low potential to a high potential and then letting them go. Okay, and what that process is, in the case of batteries, it's a chemical process. In the case of solar panels, which is another way to generate energy, it's literally light physically knocking, like a light beam comes in, it hits a solar panel, and it literally knocks out an electron. And that electron then it gets some energy, right? So that's another way you can do it. Is you can have a solar panel and it just kicks the actual charges off. In addition to that, go ahead.
So these electrons are this battery is like basically positioning electrons in an electric field that allows them to do work.
Definitely. So within the wire itself, if we were to look at a piece of this wire right here, what we'd find, like if we blew up a section of this wire right here, what we'd find is within that wire, there would be an electric field, right? Here, yeah. So there's an electric field within the wire that's going to point basically in the direction that the kind of away from the positive charge out here. So there's an electric field in the wire, and of course that electric field can basically push the charges. Yeah.
Okay.
And you can even see what the size of the electric field is if you inspect this equation carefully. Because you can isolate the electric field. And what you can find is that the size of your electric field is going to end up being equal to delta V divided by the length of the wire, actually.
It's like volts per meter.
Yeah, it's volts per meter. That's actually another way to use the... That's another... Oops. That's not what I meant to do. Yeah, so the size of the electric field is equal to the potential difference between these 2 points divided by L, basically. So yeah, it sets up an electric field inside here. I wanted to also say that what's happening in terms of this voltage here, with a battery, it's chemistry. With a solar panel, it's light energy that kicks off the electrons. But we also have like generators, right? We also have, you can go to if your power ever goes out, you can go down to places like Home Depot and you can purchase a generator, which you feed gas into it, and then it creates electricity, right? Does anyone have one of those at their house? Anyone ever use one of those? Power in this part of the country doesn't go out very often, right? I mean, we don't have a lot of major events, but I remember a time before I ever moved to California when like brownouts were really common out here, when the grid was under like really heavy load, that you'd have something similar to what happened in Texas during this recent ice storm, where you'd have like rolling blackouts to make sure that everybody could use energy at least for some portion of the day. In situations like that, having your own source of energy is really good, like a generator, right? But go ahead.
Wait, about those solar panels? Wait, is it the same process? Not the same process, but is it like fluorescence? Is that what's happening in solar panels? Like the electron? Okay.
I'm not sure, but I'm reasonably certain those are two different processes.
Okay.
Reasonably certain. Now, the thing that happens in solar panels is called the photoelectric effect. If you want to go read more about it, the photoelectric effect was first discovered in, I don't know, the late, like the turn of the century, the late 19th century, like 1890s, something like that. So they discovered this effect that if you shined light on a piece of metal, certain types of metals, that you would get you could create electricity basically. And it was a really interesting phenomenon that people couldn't really describe really well. They're just like, why does light actually kick off these electrons? But they were less. It was less about why and more about the how of what was going on. Because when they set up these experiments to try to understand and control this process called the photoelectric effect, they found that there were a lot of problems, such as that when they wanted to increase the effect, the way that they did it was really surprising to them. It turned out that it was the frequency of the light and not the intensity of the light that actually kicked the electrons off. I don't know how much more detail you guys want me to go into this, but
Pretty interesting.
yeah, it's like the analogy that's often used is this. Imagine that you've got someone in a boat, they're on a canoe, right? And they're in like a wave pool, and you can control the waves, right? And your goal is to knock the person out of the boat. So, person sitting on a boat, imagine calm water, the boat's not going to tip over, right? Now, probably the easiest way to knock someone out of that boat is just to create really big waves, right? If you have huge waves that are like 12 foot from top to bottom, then it's probably going to topple someone sitting in a small canoe. Does that make sense? Do I need to draw something?
Oh, yeah.
You guys are following? Okay. So you'd think with light, if you shined a really, really like intense laser beam and cranked up the intensity so it was just a huge, super powerful laser, and you shot it at a piece of metal, that should knock off more electrons. In the same sense that if you have really big waves, it's going to knock over your person in the canoe, right? That's not what happened. For certain frequencies of light, you couldn't knock off anything, and they would switch the frequency by just a little bit, and all of a sudden a huge stream of electrons would come out. And the fact that it was frequency dependent was really surprising. So no one could figure out this problem until Einstein solved it, and he wrote a paper in 1905, and he described what was happening with the photoelectric effect. And in order to describe what was happening, he used a new idea that was presented by a guy named Max Planck, or Planck, I don't know how you want to pronounce it. And his idea was that energy is really only delivered in kind of packets, what he called quanta, little tiny pieces of energy. And Einstein used that concept to explain the photoelectric effect, and it was really kind of the big, I don't know if it's the right way to say it, but it was definitely one of the major factors in making people realize that classical physics did not describe the subatomic world very well. That the physics we're learning in this class, it does not describe electrons very well. It does, like it describes electrons moving in electric fields and stuff like that. But at the actual subatomic level, with the way that electrons interact with the nucleus and stuff like that, it doesn't explain it. It doesn't explain it. So yeah, that was part of like what drove quantum mechanics. Was trying to explain how solar panels work, basically, and the weird behavior that no matter how bright you made the light, you couldn't kick off any electrons unless you switched the frequency up to a threshold frequency. And then once you got past that frequency, you could actually start to crank out even more charges out of it. And you could make your solar panel more efficient in that sense. So anyway, that's just to say that's one method of generating this type of voltage, this type of energy, right? So there's the chemical method, which is batteries. There's the method by which you use solar panels, but there's also a method by which you can use things like wind turbines, um, uh, what's it called? Like hydroelectric dams, fossil fuel generation, and all of these use the same process, which is the idea of rotating a magnet near a wire uh, and using that motion of the magnet to basically push the charges around. Okay, so different ways, all to produce the same thing that you all know as electricity, right? And at the end of the day, people often don't really care how they get their electricity or how it's made. They just want to have it, and they want it to be cheap, right? So that's why we use all these different methods. Of course, these days we're trying to, some places are trying to move off of fossil fuels as a method of generating energy and switch over to things that are more renewable. Things like wind energy, hydro dams are really good, but you can only dam so much water. People are also using turbines that you put into the ocean to get the motion of the tides to make the turbines rotate, and those can also produce energy. But one of the fallbacks, or one of the flaws, I should say, of generating only renewable energy is that you are at the kind of beck and call of Mother Nature. So if the wind isn't blowing and you're relying on wind energy, you better have a lot of energy stored up. If your dam dries up, your water dries up, then you're not going to have your hydro dam working. So one of the biggest problems is that in order to truly have like renewable energy, at least with our current like technology, you also need to have some nuclear energy to go with it. And I don't know. What do you all think? Are you scared of
I,
nuclear energy?
I was just about to say, like, I think nuclear energy is going to start making like a stand. I mean, because the world's energy consumption is, not going down, it's just going up.
Mhm.
And we're going to just need more energy. I mean, for like research and computation and, solving problems takes a lot of energy to do that. And I think nuclear energy, it's scary to the population
Yeah,
when
I
they
think
think they,
I think there's not enough education or people are not educated that much about nuclear energy because technically nuclear energy does create the most energy, right? Or most voltage for everything. I believe so. But
It,
of
it
course,
it creates a lot of energy for a very small amount of input mass, right? You have a very tiny amount of fissile material, which is material that can do some work for you basically, and yeah. The drawback is that you generate a lot of nuclear waste, and we don't really know what to do with it other than just bury it underground, which is literally what they do.
right, that's another big issue that we do have a lot of nuclear waste, but I think everything does have a side effect no matter what
Right.
with energy. As you said about renewable energy, wind turbines, solar panels, and then as well as fossil fuels. So, I mean, that's like the
yeah,
fate you could go
we're
through.
just going to like smog ourselves out of existence. Or like, the thing is with like fossil fuels, it's like, oh, it's so easy because you don't have to like really kind of physically, well, deal with it in the short term because it's like, oh, it just goes into the air. So it's like, oh, it's someone else's problem.
Yeah, definitely. And of course, we're finding out that it turns out that it's everybody's problem, because
Hmm.
as we dump more and more carbon into the atmosphere, it's heating up the planet. And what makes nuclear waste hard to dispose? Well, you can't just throw it in the trash can because the nuclear waste often still has some radiation coming off of it. And so, if it were to get near people, it could cause a lot of like damage to your tissue, i.e., it could like cause mutations or burns. So you can't have it really near people, and you also really can't have it near water sources because you could irradiate the water source, which could produce free radicals and different things that could cause harm to your body when you drink the water. So you need to make sure, yeah. So you can't just go dump it in the lake, right? And you also got to make sure that the groundwater isn't affected by it either. So I think they usually encase it in like a bunch of concrete and then just bury it underground. Um, and then the biggest problem is that the 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 radiation coming off of this nuclear waste, I believe that it's going to last for, in some cases, maybe thousands of years before it becomes like inert. You know, you learn about in your you guys learn about half lives in your chemistry classes,
Yeah.
Yep.
right? So if the half-life of the thing you're trying to dispose is like 50 years or something like that, well, that means after 50 years, half of it's gone, and you can do a calculation to figure out how long is it going to be before there's nothing left, and it could just take a really long time. Does that answer your question to how? Just basically, and I'm not a nuclear scientist. I'm a particle physicist, but I should know more about it. But there's only so much I can remember from the things I study, so sometimes I have to go look this stuff up. But I think I hit on. There's probably literally I can give you the surface level explanation, but that's a great question. If you go look on YouTube about some things about nuclear waste and how to handle it and stuff like that, you probably go down a serious rabbit hole of just finding all kinds of different ideas about what we could be doing, and I don't even know what the most modern ideas. How about we just shoot them to the moon or space? Well, it costs money to do that, for one. It costs a lot of money to lift things into space, but I suppose that could be one thing that we could do. Shoot them to the moon. I don't know. Is that a good idea? We've already ruined this planet. Do we need to ruin another celestial body by dumping our trash?
It is expensive.
It's really expensive to lift things into space, yeah. But it's getting cheaper, right? Because you have these. You've got a lot of corporations now, like Blue Origin and SpaceX, that are actually providing ways that people can get things into space. Obviously these. Anyway, certainly an idea to how you could definitely consider that being a possibility. But I hope that Cam's right. I hope that people's attitudes change on nuclear, because even though we've had some obviously really bad disasters, and in your lifetime, you all probably remember the Fukushima disaster, right? Where there was an earthquake or a typhoon in Fukushima, Japan, and due to this, their system wasn't prepared, and a lot of people died. A lot of area was turned into a toxic wasteland or whatever, not safe for people to live. Anyway, these events are pretty rare though, and usually it's a mechanical or engineering issue that the way that it was constructed wasn't prepared. And there's all kinds of new types of nuclear reactors that we could be building. Unfortunately, you need to have public will behind that, because to get these kind of things like nuclear plants actually built, so I don't think they're usually done by private contractors. I don't know about that, but it usually takes. And of course, people don't want to live by the big nuclear silos because it's kind of scary. But at the end of the day, we're gonna have to find some way to start using nuclear if we actually want to wean ourselves off of fossil fuels, because it's extremely unlikely that we're going to be able to get off of fossil fuels without some kind of reserve way to produce energy. And the idea would be you wouldn't even turn on the nuclear reactor until either, one, the demand spiked so high, let's say, for example, in California during the summertime when it's really, really hot and people are jacking up their ACs and, all that kind of stuff. You might need to turn the nuclear on then. And then the other time to use it would be when your demand was normal, but your supply of power coming from the renewable sources dropped because the wind was low, or because it's been dry for a really long time and you're not getting as much power from your electrodams, your hydroelectric dams.
Are we all, when we say fossil fuels, are we also talking about what about cars and gasoline?
Sure. I mean, when your car burns gasoline, that's a type of fossil fuel. Sure. Yeah. Why would we not? What are you thinking?
Well, there's a difference between cars and house electricity, and by difference I mean people are going to be driving, or what are we going to do for cars now? Because I don't think we could maybe a nuclear reactor in a car. Mm-hmm. I feel like that would maybe take a different response.
It's probably not something we're going to have anytime soon, of having a nuclear reactor inside of your car. So yeah, you just have electric vehicles, like Jacqueline's saying. So one of the things about fossil fuels is that they're not really inherently bad unless you just burn them at extreme levels and just dump tons and tons of stuff into the air. That doesn't mean we wouldn't still have fossil fuels to run our rockets, right? And ideally, if we stop using so much oil and gas to provide energy for us, we could use it then to drive our cars around, right? Because it's a really handy way for cars, right? Obviously, the idea of the electric car has been around for a really long time, but commercial electric cars haven't become popular until recently. And even now, like maybe 1% of the population is driving them. So, yeah, it'd be really nice if we could save all that oil and gas just when we need to drive on really long hauls, right? Because electric vehicles, they can only go like what, like 300 miles, like the best ones right now, before they need to recharge.
Right. Tesla has like 400,
When I
410.
mean, when I was in college, I had a Dodge Neon. This is like a 1995 Dodge Neon, if anyone remembers that car. I don't know if they make them anymore, but it was extremely efficient. And when I would drive across the country on one tank of gas, I could get like 550 miles. You know, I could basically go all the way from Tulsa, where I lived, to Albuquerque, where I was going to school. I was in Santa Fe actually, but that's really nice, right? Being able to carry that was only like a 10-gallon tank too. On a 10 gallons of gasoline, I was able to go really far. So, yeah, I think gas cars will always have a future for like really long haul trips, for like truckers and stuff like that. Jess, you're making a lot of noise. You could. I'm just gonna go ahead and mute. If you can, I'll just.
You're making a lot of noise.
Okay, Jess, I just server muted you, so maybe you can figure it out during the break, and I'll unmute you during the break. But yeah, Jacqueline, that's
Also,
a really,
methane.
interesting question. Though. What's up?
And also it's not just like fossil fuels, but I've also heard that methane from like livestock and animal farming is also
So that's
a pretty
another
big
type of.
producer.
Yeah, that's another source of.
But I was reading an article saying that even though we do go most electric, it will make a huge difference. It will, of course, lower down the or help climate change, but it doesn't have a huge impact on it.
So I'm interested.
Is that true?
I'm interested to know what the article said, because it depends on how you charge your electric vehicle, right? Like if you're charging your electric vehicle by plugging it into your wall socket at home, where you don't even really know where the power is coming from, chances are it's probably coming from fossil fuels, right? So if all you're doing is burning fossil fuels at a power plant and then using that power to power your electric car, you're still polluting, basically. Probably just as much, maybe less. I don't know. Depends on how efficient your car would be compared to how efficient the power plant would be, right?
Right.
But if you're like,
I think
go ahead.
I was gonna say that's kind of the issue right now is charging and all that type of stuff. It has a huge impact, right? If you're gonna own an electric car, you gotta know where to charge your car and all that. Well, I mean, Tesla has the superchargers and everything, but you don't even know also where the power's coming.
Yeah, exactly. You don't know where it's coming from, right?
Yeah.
And
Makes people feel good.
you definitely can have, like, I have some friends that have a home.
I'm asking out.
You're still making noise, Jess. Yeah, just try to
Oh
turn
my
on.
God.
Just turn on push to talk. It'll probably fix it. All right. So what I was gonna say is that like I have some friends. He's an engineer. He lives near San Luis Obispo, and they've got a gigantic like solar panel network on their roof, and they use solar for all of their power, and they charge their electric vehicles with solar. So if you're doing that, then yeah, like the electric vehicle is 100% gonna help. I don't, Prince Ali. What did the article say about stuff like that? If you're getting your electricity from the sun?
It was like a really old article. It's like about like 2 to 3 years ago when like the whole entire climate change started like to rise up, and that how every country pairs climate agreement and everything kind of just blew up.
Okay.
But I think it was from one of those electric companies too. One of those electric articles. They just focus on pure like electricity and all that stuff.
Okay.
Articles, but I don't recall a lot of it. But I remember just explaining how that what you're basically saying about how we don't know where the energy is still being burned from, and they're burning mostly from fossil fuel because right now we're heavily reliant on fossil fuel.
Absolutely.
So it's still a very bad thing.
Yeah.
I mean.
Okay, Kyle said. Go ahead.
No, go ahead.
Kyle said, doesn't a big majority of pollution come from manufacturing goods? Probably. Yeah, I don't know right now what I think what Cam said is one of the biggest ones from my yeah, Jess, I'll help you during the break to fix that. But I think one of the oh, here we go. We got a little graph here. What is this? Where they come from? So transportation looks like the biggest one. Solid waste disposal, industrial. Okay, so this is just pollution in general. So it's not necessarily just air pollution, right? Yeah, it looks like
Isn't there a way where you can also like
carbon dioxide
Are-
isn't even on this list actually. It's interesting.
is there like ever a way where we can like use garbage as like to power electricity? I think I saw something like
We do at a lot of the trash plants. So I'm from a little town in Oklahoma where I used to drive by what we called the trash to energy plant. That was the name of it, and it was literally a place where they burn trash to make energy instead of burning fossil fuels. So yeah, you could totally do that. I went to visit it one time. It was really gross. Like there's a big wall of trash, and you could
is
see
there
what's
the negative side of it?
milk cartons and stuff like that. Well,
Wouldn't it be
it's still polluting. I mean, you're burning like plastic and
Yeah.
stuff.
Oh,
I was gonna
So
say,
if you've ever accidentally burned a piece of plastic in the microwave or like accidentally set a piece of plastic on your
terrible.
stove, it's not good. It's not good. So that's what that place smelled like. But I think they said that they try to like they have a filtering process or something, but they can't get rid of everything. So yeah, I mean, this was in a very industrial part of town that I happened to drive through. Like it was like railroad tracks and oil refineries and this trash energy plant there was too. But yeah, I think that's pretty common that a lot of the trash facilities where it's not just a dump, that they try to produce some energy out of it to recoup some of the cost, to make some money off of it, right? Because then you can just sell that energy back to the grid, and you can also use that energy to run the plant. So yeah.
Just have another pandemic to help pollution.
Is the pandemic helping pollution?
Yeah,
I think
actually
so.
doing a
Yeah.
lot.
Because people aren't driving as much or whatever?
Yeah, like
Yeah,
the air
during
got
peak.
really cleared in downtown. Like it was actually good. There's no smog.
Yeah, I did hear about that, Jacqueline. I think that's really cool. So it's we're not allowed, like, what is it, by 2035 they won't be selling, assuming that the order stays in place and there's not another governor that overturns or something like that. No gas powered cars will be sold in California, basically, right?
Mm-hmm.
I don't know.
Whoa.
Is it going to make it illegal to drive a gas powered car?
They were saying
What
by
if you
like
already own one?
2030.
You have to sell it.
I think it was
Like-
by 2030. California said something like that. The governor had this order or something about it.
Yeah, that's what Jacqueline was saying. Is it's 2035.
Yeah.
Probably not going to make it illegal. Yeah, I would agree.
Yeah.
You can't really make it
Yeah,
illegal
no
because like it's
Too many of them, right?
they might
So-
tax the hell out of it though. You may have to pay
Yeah,
like when you
gas
when you
tax.
when you
That's
go
what
get
California
your-
does best, though.
Yeah, that's right. We're really good at taxing things. That's true. God, taxes here are just so high. It's ridiculous.
It's ridiculous. Living over in California is ridiculous. So many people are moving out to Arizona or Texas.
Yep. Good. There'll be less people here then. We can all stay and enjoy the wonderful weather and incredible diversity of biomes that we have here. I love California.
The funny thing is, I mean, overall, our car market is just kind of going basically to just all wiring and all that, because all electric cars are basically is just wiring and a battery.
Mm-hmm.
So that's interesting how mechanics in the future we're gonna have mechanics in the future, right? Because it's gonna be mostly like when we want to have our electric cars repaired, right? It's not really like it's more like an electrician, not really a mechanic.
Yeah, but don't you think that the people that are currently working on, like that are currently mechanics, will just learn ways to work on the electric cars too? It's just a natural, evolution of that job, I think.
Yeah, I mean, I guess so. Yeah.
I don't know. Is anyone here a mechanic? I know my last semester I had a guy. I don't know if you guys know Eduardo Alvarez. I know he's a mechanic. I should ask him. Electric cars are a lot easier to work on. That kind of makes sense.
It's less moving parts. So
Just one gigantic battery. Although the batteries
There's a lot more
eventually-
wiring that goes into it. That's a huge effect, though.
Yeah.
So you really gotta know your wiring and all of that, circuits and everything of that sort.
Yeah, for sure.
So I mean that's a heavy skill that you need to have, and I think that's why eventually. I mean, I know Tesla itself. A bunch of my dad's friends owns Teslas as well, and their pricing. I mean, in general, just maintenance for that's expensive as heck, especially the battery itself.
Yeah.
Replacing the battery is
So-
expensive.
Oh, absolutely. The battery itself is like incredibly expensive. Is it worth it anymore buying new cars? Well, 2035 is what? It's 14 years off, right? So, I mean, I don't think buying new cars is ever worth it. Like, if you got a car and it works, like you should just ride it until it goes into the ground. So that's what I've been doing. My car is from like 03, I think, or something like that. What's that?